Hello, this is Reaction Mechanisms Practice Video 2. We're going to work through problem 50 on page 571. Here's problem 50. It says, the mechanisms shown below have been proposed to explain the kinetics of the reaction. Then we have this reaction, and we know the rate law for the reaction. It says, which of the following are acceptable mechanisms? Explain. So we have three options. There's mechanism 1, it's got one step. Mechanism 2 has these 3 steps. We know if they're slow or fast. Mechanism 3 has 2 steps. We're supposed to say which of them are acceptable, which kind of makes it seem like maybe more than one could be acceptable, and we're supposed to explain. All right, so we need to check each one and decide if it is plausible. And there's 2 requirements of an acceptable mechanism. So one requirement is if you add up the overall steps, so if it's just one step, it's just one step, but if there's multiple steps, if you add up the steps, you cancel things that are the same on the opposite sides, you put things together if they're on the same side, you add up the steps to get the overall reaction has to be the same as the actual reaction you're trying to get. So that's the first requirement, is the overall mechanism, or the overall reaction has to match the equation. All right, and then the other one is that if you have the other requirement is that the slowest step of the mechanism has to have its reactant's molecularity give you the rate law of the reaction. So remember how if you have elementary steps, you can take the reactants and change the reactants to mean the rate law. Now, in a mechanism, every step is an elementary step, and it'll always tell you which one is slow, and the slowest step is called the rate determining step, because that's the only step that affects the rate law. All right? So the first requirement of a mechanism is that if you add up all the steps, you have to get the actual equation, and the second requirement is that the slowest step has to give you the rate law. So you can call this rate determining step. All right. So let's just go through each of these and check what their overall reaction is and check their rate determining step and just see, could they be consistent with the actual, with our actual equation and our actual rate law. All right, so let's start with mechanism 1. Mechanism 1 only has one step. So the only step is equal to the overall reaction because, you know, there's nothing to add up or subtract or combine because there's just one step. And we can check, and it does look like the reaction here is the same as our actual reaction. So we can say, yes, the overall reaction does match the equation we're trying to get. Now with the rate determining step, if there's only one step, then that's the slowest step. So we can look, what would the rate law be if this was our rate determining step? Well, you only look at the reactants. So you could say rate equals K, and then we would write our reactants and their coefficients become exponents, so it would be H2 squared times NO squared because of the 2's, the coefficients of 2. And that does not match our rate law. It doesn't matter what order you write it, but our rate law should be first order in H2, and this one is second order in H2. So this is not a good mechanism. No. All right, let's check mechanism 2. Okay, so this one has multiple steps. So if we want to figure out the rate law, we have to find the overall here. So what would I get if I added all these up? Well, let's look for things that cancel. So I see plain nitrogen is here and here. Or we can say it's here and here. So if it's on opposite sides of the arrow, that means it cancels. All right. I see the same thing going on with the one atom oxygen, there and there. So those cancel as well because they're on opposite sides. All right, the other thing you can do is look for things that are on the same side, because those are going to combine. Like on the left side, I have H2 in 2 places. So that means that they will combine. So instead of just writing H2 in my overall reaction, I would write 2H2. Okay, same goes with NO on the left. We have 2 of them. They're both on the left, so they will combine. So on the left side of our overall reaction, we have 2NO. All right, and then we can draw our arrow, because that's everything on the left, so it's everything on the left of our overall. Here on the right, we have only one N2, so there's only one N2, but we have 2 H2Os. Did I say left? I meant right. Here on the right, we have one N2, and there's 2 H2Os on the right. So we'd have 2 H2Os on the product side. So this is our overall reaction, and we have to go up and check, does it match the reaction that we're given? And it does. And again, it doesn't matter what order you wrote things. Like if I had written 2H2O plus N2, but that's still on the right side, and then it's in this order up here, it still is the same reaction, because it doesn't matter what order you put those. But it's the same number of each molecule on the left side and the same number of each molecule on the right side between the actual equation and the overall. All right, so the overall reaction is good. Let's check that rate determining step. Okay, so the rate determining step is going to be the slow step. And the only reason we know that's slow is because it says it's slow. That's something required in the mechanism. All right, so we're looking at just the reactants of the rate determining step, so just this H2 and NO. Now neither of those have coefficients, so then the rate law for this mechanism would be rate equals K times H2, would have a coefficient of 1, so it's to the first power. We don't have to write a little 1 up there. We don't write that, but that's, you know, thinking about it there, times NO. And that would also be raised to the first power, because those are the reactants of our rate determining step, and they don't have coefficients. Now this does not match, right, because the actual rate law is supposed to be second order with NO. You have first order at NO. So mechanism 2 also cannot be correct. So we're going to hope that mechanism 3 can be correct, but it's always good to check, right? So let's first go through and find the overall reaction. Might make sense to pause it and see if you can figure out the overall reaction yourself, and then see my answer. Up to you. All right, so here we go. What if we add these up? Looking for things that cancel. Looks like N2O would cancel. All right, and I don't see anything else that cancels. All right, so we've got our reactants. We have H2 plus 2NO and also another H2. So the H2s would combine, and then we still have the 2NOs. So basically I'm just writing anything that was on the left side of any step all gets combined to be the left side of your overall. Okay, and then on the right side, we've got an N2 and 2 H2Os, so we can write N2 plus 2 H2O and compare this overall reaction with the equation we were hoping to get, and it is the same. So far so good. But remember, there's 2 requirements of a mechanism. The overall reaction has to be correct, and the rate determining step has to give you the rate law. So let's look at that rate determining step. It's the slow step, so it's step 1. It's not necessarily always going to be the first step is the slow step, but just in both of these examples it is. It could be any step that says slow is your rate determining step. All right, so we have our reactants here in the rate determining step. We have 1 mole of H2 and 2 moles of NO. So the rate law from that would be rate equals K times, we have H2 with a coefficient of 1, so it's H2 raised to the first power, and then NO would be squared. All right, and is that the same as our rate law? It is. They wrote it NO squared times H2. I wrote H2 times NO squared, but remember, it doesn't matter what order you put things, it's just the order, right? What are the chemicals and what order are they raised to? And then this is a match. All right, so that means that mechanism 3 is plausible. All right, so it's acceptable. All right, so we can write our answer. Only mechanism 3 is acceptable. And it says we're supposed to explain, so we can say the steps add up to the overall equation, and the slowest step is consistent with the rate law. It's important to realize that although this is an acceptable mechanism, all that means is it's possible. Mechanisms are always guesses that we can make based on what we know about the rate law and what we know about how reactions might go, but you can't ever test them, so it's just theoretical. All right, that is all. Thank you.